Welcome to the BAA Christmas webinar. This is being held on Zoom and live streamed to YouTube. We are recording the webinar and it will be available to watch on our YouTube channel a few hours after the meeting, as with all our other webinars this year. It is my pleasure to hand over to Alan Lorraine, the President of the BAA. Alan, you're still muted?
You didn't unmute me, Andy. Okay, thank you very much indeed, Andy, and a very warm welcome to the BAA Christmas lecture and season greeting to everyone as well. So this is the first meeting for the new session of the BAA. It started in October, and obviously the last one for 2020. And as Andy's alluded to, that we are broadcasting on YouTube and by webinar because of the obviously the COVID restrictions. We have been told by the Institute of Physics, where we would have hoped to have held today's event, that they are likely to be closed probably for the first half of next year, but we're keeping the position continuing under review, and we hope to get back to being able to meet with each other on a face-to-face basis as soon as possible. Having said that, we will, of course, we will continue to live stream them for those members who are unable to or unwilling to attend in person. So before I pass over to Emily in just a second, one of the privileges of the President is to be able to present the awards that the BAA offers. And one of the latest awards is the Sir Patrick Moore Prize, which generous donation was made to the BAA with a request that we set up a prize, which we have done. Details are available of the criteria of the prize, but essentially it's in line with Patrick's ethos for the encouragement of public interest in astronomy, contribution to understanding of the history of astronomy, outstanding observational work for somebody who is under 21, the encouragement of participation in observational astronomy by youngsters, and finally carrying out of collaboration work either just with amateurs or in conjunction with professionals. People can be nominated, either individuals, groups of members, or even affiliated groups. And there is a committee that looks at these submissions and then chooses the person to whom we are going to award the prize, and that comes before council for approval. We did that in October, and I'm very pleased to announce that Rita Whiting from the Crayford Manor Astronomical Society has been awarded the prize for this year. It's in addition to the certificate, and I have here a certificate. There is also a £500 prize as well. Now, what I was hoping to do was to have Rita on the call today as well, and to be able to say, here's a certificate. Oh, there you are, Rita, and for her to then take and produce one at her end. Unfortunately, she doesn't have a facility for a camera, so all I can do is to say congratulations to Rita for her exemplary work in promoting observational astronomy amongst a wide group of people, and for that, it's a just reward that sort of you've been given this prize. Well, I'm speaking to Rita this morning, and in actual fact, of the money that she's been given, she has actually spent that on some, I think they're called Mira globes. They're small globes which she's got Jupiter, she's got Mars, and she's got the Moon, and they rotate. And basically, she bought them for outreach opportunities with both the BAA and Crayford Manor as well. So justifiable sort of winner in this case. So without further ado, I would just like to introduce to you Dr. Emily Blunsdon. She is a lecturer at the University of York, where she's a teaching-focused academic specialising in inclusive practice. She specialises in astroseismology, and she is also director of the Astro Campus, a teaching and outreach observatory at the university. And Emily has regular outreach activities and co-hosts the podcast Synergy, which discusses astronomy news, research and other exciting topics. And I understand that she's off to New Zealand on Friday in connection with various collaboration projects. So without further ado, fantastic planets and how to find them, Dr. Emily van Brunsden. Thank you much. Over to you, Emily.
Thank you, Alan. That's very kind. Yes, so to kind of briefly, I guess, introduce my astronomical side, I'm going to share my screen, which is kind of about the talk that I've got here. So you can see my lovely slides. So yeah, as an astronomer, my research interests are mostly in stellar physics. So you might have noticed from the talk, I'm actually going to be talking a lot about exoplanets today. But really, the work that I do in stellar physics is really, really closely related to exoplanets. And in fact, we're probably two of the closest research communities that are working together for a total understanding of exoplanets or planets outside our own solar system. So I work kind of mostly in the star side, and then lots of my colleagues work on the more sort of planetary focus side. So in a bit more detail, I'm a spectroscopist by training. So I do most of my work in high resolution ground-based spectroscopy on fairly large telescopes. But I have transitioned in the last sort of 5 or 6 years into some more space-based photometric observations as well. I'm going to be talking mostly about some of those today from the new space telescopes that are up flying, looking for exoplanets, but I also use them for work on variable stars that I do as well. So hopefully today you'll get to see a little bit of how my work intersects with this other kind of fascinating area, which is looking at exoplanets. And when I put this talk together, what I really wanted to do is kind of have a bit of fun with it and play around thinking about, you know, if these are really wonderful exoplanets that we are discovering, can we take the next step and imagine what it might be like if we were able to travel there and visit and see some of these other worlds. So I've had a lot of help from NASA and the Exoplanet Travel Bureau, which is the sort of outreach project that they've got going there, where they've got these amazing travel posters. And so I encourage you to have a look at through the full selection, but I'm going to be showing you a few of those today as part of this talk. But really, I've just picked out some of my favorite exoplanets, and I wanted to share those with you. So if we start off by thinking about exoplanets, we have to, of course, think about planets, and the most sort of sensible planet to start from is our own planet Earth. And when we look at exoplanets, we're looking for very often things that are very similar to the Earth, because I think it's very arguable that one of the biggest questions that we have as a planet, as a humanity, to understand is, are we actually alone in the universe? And that question begins with, well, if we want to find life out there beyond the planet Earth, then we need to start with understanding our own planet pretty well, and then taking those data and looking for similar features out there in our galaxy. So if we have a look kind of at the Earth, maybe from a perspective you haven't thought about it before, but from the perspective of thinking about it as an exoplanet. Now, it's helpful that in exoplanetary science, we tend to use units that are quite sort of familiar. We sort of do away a little bit with a lot of the very technical astronomical stuff. So when we think about things like masses of planets, radii of planets, we tend to base these around planets from our own solar system, most commonly Earth and Jupiter, as kind of Earth being Earth-like planets and Jupiter being sort of big gassy things. So I'm going to talk about some of their favorite planets, and I'm going to have some key data, things like the mass and radius is expressed in terms of our own planet or planets in our solar system. What's also very important, and of course from my perspective as a stellar astronomer, is looking at the star. And the star tells you everything you need to know about the relationship between the energy, I guess, transfer between the star and the planet. So the temperature of the star and the distance that the planet is from its host star are both really, really important parameters. So in our case, we've got a sun as our star, which has a surface temperature of something around 6,000 Kelvin. I mean, when you get up into the thousands of kelvins, it's pretty much, you're talking about 6,000 degrees. It's more or less the same. And we are at a distance of about 8 light minutes from our sun, which means light takes about 8 minutes to reach us. And I'm going to kind of use the distance between the Earth and the sun as kind of a foundation stone to compare other exoplanetary systems as well. We do have a term for it, it's called 1 astronomical unit. Now, the other thing I had a little bit of fun with when I was putting together this talk was that I thought about, okay, if we're going to think about going to these other exoplanets, what would it actually kind of be like if you were to put a holiday brochure together and put some kind of figures on that kind of holiday? And this is where I have to confess, I went down a little bit of a rabbit hole and got a little bit nerdy about thinking of calculating distances to planets and figuring out how much it was going to cost. And the first thing I wanted to sort of figure out was actually what's the cheapest way that you could get to an exoplanet. So I compared things like what is the price per kilometer if you fly, what's the price per kilometer if you drive, if you go take a ship, all these guys have sort of got a little bit carried away. But in the end, I decided it's probably most cost effective if we drive using I guess a pretty reasonably fuel efficient car. So if you can get something like 60 miles per gallon from your vehicle, then actually it turns out driving to an exoplanet would be the most cost-effective way. Now, I don't think that's necessarily, of course, at all possible, but it kind of gives us a bit of a sense of scale, because if you were to drive with your moderately efficient car to the sun from the Earth, then it would cost you something like £7 million in fuel. Now, that's not particularly a strange or out of this world number, because actually that's pretty comparable to what it would cost to launch a satellite, for example, around the Earth. So I think, although the numbers are kind of quite fanciful, actually, when you think about them in that kind of context, they kind of make a little bit of sense. So then we sort of think about looking at our Earth from sort of a few steps away. We know that there are lots of features about Earth that make it habitable, but really it's these key ones that when we're searching for exoplanets that we want to nail down first. Things like finding out if there's water on a planet, if it's got atmospheres, if it's got any kind of chemicals like methane and things so on. They're actually really, really difficult to understand. And we're really only at the point for most exoplanets where we're just getting the basic data, and we're going to kind of work on getting more detail in the next generation of space telescopes. So going from the Earth, I thought it would be nice to share some information about what I guess feels like a long time ago, but in a sense, in kind of research astronomical terms, is actually not very long ago, which was the discovery of the first exoplanet. And by here, I definitely mean the first exoplanet to be going around a kind of a normal sun-like star. And this, the planet with this great honor is called 51 Pegasi b. So it's the B means the planet around the star 51 Pegasi. We don't start planets with A, we start with B, lowercase letters. You might have come across, for example, when you have binary star systems, we tend to use uppercase letters. So you might see an uppercase A and an uppercase B. For planets, we use the lowercase and we don't use the A. Still haven't quite worked out why we can't use the A, but it just seems to be the way it's forward now. So 51 Pegasi b actually has a new name, which has got named a couple of years ago. It's one of the few exoplanets with a name, and it's called Dimidium. It's actually a surprisingly mysterious exoplanet. We don't have a very good sense of exactly how big it is or exactly what its mass is. We think it's probably at least half the mass of Jupiter, but it could be quite significantly more than that. And the reason why we haven't been really able to nail this one down is because it is actually quite a difficult one to measure. So I think what we sort of found in exoplanetary science is that the more we search, the more weird and wonderful things that we discover, and the more surprises we tend to have along the way. So this planet, which is at least half the mass of Jupiter, for example, is found orbiting something like 1/8 the distance that Mercury orbits from its host star, which is just, it was completely unheard of. We hadn't even considered that if we were going to go out and find exoplanets, the first one we would find would be a crazy big planet, insanely close to its host star. Because as far as we understand planet formation theories, these kind of planets just shouldn't exist. So to have the very, very first exoplanet to break our planet formation theory was quite exciting, really. We now call this type of planet a hot Jupiter, and we've found quite a few of them, not necessarily because they're common, because they're actually pretty rare, because they turn out to be quite easy to find. Big planets close to their host star means that they have quite a large effect on their host star, and it's by and large, the effects on a star that we are measuring when we're trying to find these exoplanets. So if you have a big effect, it just makes you a bit easier to find. Now, the most exciting thing is this exoplanet was discovered in 1995, and actually last year was one of the planets for which the team won the Nobel Prize for the discovery. So kind of a very, very famous classic exoplanet, I would say now. So although a hot Jupiter may not sound like the perfect kind of place to go for a holiday, it is at a sort of moderately sensible distance of about 51 light years away, which means if you were to drive your kind of sort of sensibly fuel efficient car there, it would only maybe cost you on the order of 15 trillion pounds, which isn't too bad when it comes to at least scales in our own galaxy. And I think it might be worth it to go and sort of find the original, and now even more excitingly, the Nobel Prize winning exoplanet. Now, I'm going to go to another sort of very, very hot exoplanet, and this one's called 55 Cancri E. And this is another planet which has actually got a proper name. Its proper name is Janssen, and it's orbiting around a star called Copernicus. Now, it might sound like astronomers have kind of just gone a bit crazy and started naming exoplanets. And we've got thousands of exoplanets that we've found. In fact, as of today, when I checked, we've got something like 4,307. Now, that doesn't mean we've been sitting here sort of all the way through lockdown, dreaming up new names for all the exoplanets that we've found. There's actually only about 50 exoplanets that do have proper names. And these were chosen in a competition. And so there was kind of a I guess, crowdsourcing competition to start to name some of these exoplanets. And Janssen, and going around the star Copernicus, was one of the winners for 55 Cancri E. Now, why I think 55 Cancri E is a really interesting planet is that you'll notice it's not the only planet in its system, because it's E, which means they found B, C, D before they found E. But I think it's actually a very exciting one, because this is an example of a type of planet that we don't have in our solar system. And it's the type of planet that really seems like it's jumped out of a novel. It's an entire planet which seems to have a surface which is lava. And that's pretty amazing to think about, because I remember when I was a kid playing, the floor is lava, let alone playing the whole planet is lava. It seems like just an incredible thing to try and imagine. So to be a planet which is lava-like, you need to be kind of rocky, kind of small, but like the Earth, or in this case, about twice the size of the Earth, but more heavy, so it doesn't have the atmosphere that the Earth does, just kind of rocky. But it's very, very close to its host star. Although the host star itself isn't super hot in terms of sort of star temperatures, it's pretty close. So that means that the whole surface is kind of molten. There's some really, really exciting things you can think about with these lava worlds, and how the lava moves around the surface of the whole planet. And there's even some visualizations at the Exoplanet Archive where you can go and kind of land on this planet, although landing on lava is maybe not the best idea. But I like how NASA's kind of reimagined this to be a holiday where you can sort of enjoy your lava world from the safety of your own sort of bubble high above the surface, which is pretty cool. So to have such a kind of planet as lava experience, you're looking at traveling something like 41 light years away from Earth. So even slightly cheaper than 51 PEG, which is about 12 trillion pounds to get to Janssen, to get to 55 Cancri E. So I know that this talk is called Fantastic Planets, but it's also how to find them, because it turns out that the techniques that we've been using to find exoplanets have really gone above and beyond, I think, what anyone ever expected. Even in 1995, when we first started discovering these planets, we never really imagined that in 2020 we'd be in the position to say, yeah, we've got thousands of these things now. They're fairly easy to pick up. And most of that is actually down to a single space telescope, which is Kepler. And Kepler flew in its main mission from 2009 to 2014. And Kepler's a photometric space telescope. So the idea with Kepler was that it would sort of point at a sort of patch of sky, a fairly boring patch of sky, really, in Cygnus, and monitor something like 100,000 stars for 4 years, And let's just see if we can pick up from the photometry, from the light that's emitted from these stars, if we've got any transits. And a transit is just a small dip in the light that occurs from a star when a planet passes in between the star and us. So we see just a little bit less of the light from the host star because the planet's blocking it out, in the same way that we have transits of Mercury, transits of Venus, etc. Now, this sort of graph of how a transit works is grossly over-exaggerated. The size of planets and the size of stars and the relative distances between them mean that most of the time we're really looking for drops in brightness which are less than 1% of the brightness of the star to begin with. And that's before you even try to take account of all the kind of observational factors, including the effects of the Earth's atmosphere. So this explains why it kind of took us so long to get to looking for transits of planets when we've been looking at sort of light variations from stars for hundreds of years. It's just purely that we didn't have the technology to be able to detect such small variations. So it took something like Kepler to get up there and do these very, very sensitive observations over a long period of time. And it's still down to Kepler that we know of most of the exoplanets that we still have that we're investigating today. So Kepler discovered on the order of 2,400 of the 4,000 exoplanets that we know of. So it really did a fantastic job. And the point of Kepler, it really had one sort of scientific question that it was trying to answer. Because when it flew, we didn't really know what to expect, how many of these transits we would expect to see. And that's, of course, related to how many exoplanets we might actually have in our own galaxy. And so Kepler's question was, how many planets do we have in our galaxy? Are solar systems common or are they rare? We just didn't really have any data that could tell us that. And it was only from the Kepler data that we were able to say what we can say with confidence now is that in our own galaxy, it seems that there's at least one exoplanet out there for every star. So that, of course, doesn't mean that you necessarily have every star has a planet. We've been kind of greedy and have 8 or 9 if you're still feeling a bit sad about Pluto. So, of course, it's an average, but that does mean that there's an awful lot of planets in our galaxy to go out there and study, probably somewhere on the order of 300 to 400 billion. So we've got quite a few left, I think, to find. Now, the follow-on mission from Kepler is a space telescope called TESS. And there's the Transiting Exoplanet Survey Satellite, which is the bottom picture of the 2 spacecraft here. I'm going to talk a little bit more about TESS later on because it's the current mission that I'm working on. But I wanted to kind of say, it's not all over. Kepler did a fantastic job and we love Kepler and the data that it's produced. And we are using that now to enter the next age of exoplanetary discovery. So coming back to some of the interesting things that Kepler and other telescopes have been able to help us find. So this is a really nice example, I think, of a very, very classic type of exoplanet. HD 40307G is a super Earth, or what we sort of it's really the classical super Earth of what we come to know as being actually a very, very common type of exoplanet. So by a super Earth, we mean something that's kind of just a few times the mass of the Earth. And in this case, it's sort of about 8 times the mass of the Earth, about just over 2.5 times the radius. And the most exciting thing about this kind of planet is actually we don't have anything that's even remotely similar to this in our own solar system. But we can kind of imagine what would happen if you scaled up the Earth. I mean, the first thing is that, of course, if you scaled up a rocky planet like the Earth to have kind of 8 times the mass, you're going to get an awful lot of gravity, an awful lot of surface gravity on a planet like this. So I guess from a travel perspective, this would be a really, really fun planet if you're into some really extreme kind of sports that involve a lot of very rapid descent, for example. If terminal velocity on Earth is not good enough for you, then there are loads of exoplanets that have super high terminal velocities from enhanced gravity. So, okay, it might be a bit more difficult to get up and out of bed in the morning, but I think the thrills could be quite exciting. So if this does sound like the sort of planet that you would like to go and jump out of a plane onto, then this planet is, again, not too far away, 41 light years away, and a cost of 12 trillion pounds from the last one to get to. So very, very exciting. You've got plenty of cash left over for a few of these big jumps, I think. Now, I mentioned that this is an exciting type of exoplanet because it's something that we don't have in our solar system. And what's even more exciting about it is that it turns out to be the most common type of exoplanet that we have in our galaxy. And this is, again, one of these kind of quirks of exoplanetary science. Just like the first one we found was something quite bizarre that we'd never thought of before. And it turns out to be the most common ones in our galaxy are something that we don't really know a lot about because we don't have our own to kind of investigate. Now, these super Earths are somewhere between the sort of size of Earth and Neptune, which is, okay, it's a pretty big range there. But most of the super Earths sort of sit around twice the mass of the Earth. And it's very exciting to see that these are kind of the most common because it means that you've got a lot of very, very small rocky types of planets, which are, of course, the best candidates that we have for looking for life as we understand it here on Earth. So that's quite cool that we know that lots of these rocky things are not too unusual. But it does mean that we're kind of a little bit stumped as to what exactly these super Earths are, what their composition might be. Do they have liquid centers? Do they have significant atmospheres? That's all really hard to tell when you don't have your own kind of neighboring example. What was also very exciting was that just recently we've been able to nail down that you can't have these super Earths too close to their host stars. And this is a result that's actually come out of my own sort of area of research, which is related to sort of nailing down the stellar parameters, which means that we really, to get a really good measurement of the mass or the radius of an exoplanet, it turns out you need to have really good measurements of the mass and the radius of its host star. And that, although it sounds quite easy to do, is actually really tricky and something that we've not been able to successfully do to say less than 5 or 10% very often at all for stars. But with the sort of work I'm doing in variable stars, we're actually able to tie those numbers down much, much more precisely, sometimes down to 1 or 2%, which therefore means we're able to sometimes extract a lot more detail about the exoplanets that are going around these stars. Quite exciting stuff. So they're really nice sort of syzygies between the two fields of study. Now, coming on and looking at, I guess, probably one of the most famous Kepler exoplanets that was ever discovered. And that's Kepler-16b. And this was the first exoplanet to ever be discovered around a binary star system. So this was really exciting. And I mean, you can imagine the why it got everyone, not only in the astronomical world, but of course, everyone who's a fan of science fiction really excited, because this is the kind of discovery that really mirrors what science fiction had dreamed of just a few decades beforehand. So Kepler-16b is a planet that goes around two stars. The planet itself is kind of, it's a fairly sort of somewhere between sort of Uranus and maybe Saturn in terms of size, but its orbit around these two pair of stars is what really makes it that special. Now, the two stars are quite interesting. They're quite cool stars compared to our own sun, and they're quite different stars. So whilst one star is kind of 4,500 Kelvin, the other one's about 3,000. So that means there's sort of one that's kind of quite big and yellow, compared to the smaller one, which is only 3,000 Kelvin, will be really quite a tiny star. So you get a real contrast between the two stars. So thinking about what that might be like if you're on this exoplanet, then of course you get to see two suns in the sky, two shadows, two sunsets, but from two very different types of star as well, which is quite exciting. So, of course, I have to mention that this has made people who are fans of Star Wars and Tatooine very, very excited, which means that although this particular system is really far away, so 200 light years, 58 trillion pounds, which might be getting up there in terms of budget, I think there's probably enough Star Wars fans out there to do some crowdfunding and get visiting this exoplanet. So just a couple of notes about the system, because I just find these circumbinary planets really, really exciting. Here you've got the two planets, the two stars in the system are A and B. So A is the slightly larger one, B is the smaller, redder one. And then this exoplanet is going around them both in a wider orbit again. And this is all happening within the orbit of Venus, somewhere between the orbit of Venus and Mercury. So that does mean that you will get to see this double sunset setting in the sky, which is really quite cool. So another one of my favorite planets from Kepler is also, well, it's a little bit later on in the Kepler mission that this one was discovered. And Kepler 186f became famous because it was the first exoplanet that we really found that was, I guess, similar enough to the Earth to be able to say it's a little bit like an Earth twin. And it's also in the habitable zone around its host star. So it also means that the planet possibly has a kind of sensible temperature where you might, for example, if you have water on the planet, you might be able to find liquid water. Now, in terms of sort of similar-ish to Earth, although the size is similar to Earth, it's actually only about half the mass, which means it probably has a much more significant atmosphere. And the star that it's going around is also not really that similar to our sun. So you might notice it's quite a cool star, 3,800 Kelvin. But what this means is that the exoplanet is much closer to the host star. So even though the star is cooler, the planet's snuggled in sort of closer than we are to our sun. So that means it can be a similar temperature, perhaps, as the Earth is. What's quite cool is when you start to think about these Earth twins, if you like, is what it might be like if you do change some of these parameters for Earth twins. So here you've got a significant change in the type of star that the planet's orbiting. And the main change that you see when you see the change in temperature is actually you see the change in color. So we saw this in the previous one where you had the cooler star was much redder. So this is going to be similar. This particular star is going to output most of its energy in the red part of the spectrum. Now, if you contrast that to the Earth, then you can kind of go down a bit of a garden path here of thinking what things might be like. Now, and this is not a particularly scientific argument, but I think it's quite an interesting one to sort of go through. The idea here is that here on Earth, we have plants which are mostly green. Now, that's potentially linked to the fact that the sun outputs most of its energy in the green part of the spectrum. Of course, plants are green because they've got chlorophyll, and chlorophyll is actually causing the plants to be green, which means they reflect the light back from the sun. So actually, they're throwing away the most abundant energy source, really, or the most abundant photon source from the sun. Now, I'm not really a biologist, and that sounds a little bit silly to me. If you're a plant, I would have thought you want all the energy you can, but I think it's much more complex than that in terms of actually being able to survive. But if you take a kind of tenuous argument from that and say, well, if our sun puts out most of its energy in the green, then plants on the planet Earth are mostly green. Then if you've got a star that you're going around that puts out most of its energy in the red, then could you maybe extrapolate and say that the plant life on this exoplanet could be colored red? Maybe there are different compounds that you can build a photosynthesis-like chemistry with that would mean that those plants were red. I think it's a sort of that argument in itself is maybe a little bit of a stretch too far. But this is the kind of thinking that we do have to consider when we look at the exoplanets. It's not just enough to say that planet might be a similar temperature to what we experience here on Earth, but you've got to look at the whole environment and consider how the star impacts potential life on an exoplanet. Turns out that these very low mass stars, these very cool stars, are actually pretty nasty in terms of their ultraviolet light outputs, particularly when they're quite young. So this is another way that we can sort of reframe and think, well, just because it's the same temperature doesn't necessarily mean the conditions are the same on this kind of exoplanet. But if you think that you would like to go and investigate and see whether the plants really are red on Kepler 186f, then I'm afraid that I've got bad news because this is a really distant exoplanet. Broadly, Kepler was looking at pretty faint stars, which means generally they're quite far away, and this one is no exception to that. So this one's at a distance of 490 light years away, which is a staggering 140 trillion pounds to get there. We might need a little bit of help from, I guess, biology funding in order to start heading towards that one. I guess one of the nice things that you could definitely say about an exoplanet that is going around one of these cool stars is that they will have amazing sunsets, right? Just due to the fact that the overall light output from the star itself is redder. But we do have to consider this quite a lot, because these are actually the most sort of common type of Earth-like planets that we're now finding. We're very, very good at finding things on quite short orbits. So things that are much, much less than a year, preferably on the order of kind of a few days to a couple of months. Those are the easiest types of exoplanets to pick up. So if you want them to be kind of sensible temperatures, then you need to have them quite close to quite cool stars. So that's actually one of the reasons why the James Webb Space Telescope is really focused on these cooler red stars, because those are the ones that you can actually find exoplanets with short orbits on with sort of sensible temperatures. Now, it would be remiss of me to talk about exoplanets and not talk about probably the most famous multiplanetary system, which is the TRAPPIST system. So TRAPPIST is a really exciting sort of collection of Earth-like exoplanets. And the reason why it sort of made such a big splash when these exoplanets were discovered is that it's not just got sort of a few exoplanets, it's actually got 6, maybe even 7 exoplanets that are potentially in the habitable zone of the host star. They range in mass, so some of them are quite tiny, up to kind of just over 1.5 times the mass of the Earth. And they're all snuggled in really close to, again, one of these really cool stars. And what's interesting about this system is that the star, and therefore probably the planets, are actually really old. And this is kind of one of the also sort of things you get when you look at low mass stars. Low mass stars live for a very long time, so you're more likely to find older low mass stars. And in this case, the star is at least a few billion years older than our sun. And this means that over the course of its lifetime, that it's much more likely that all the TRAPPIST planets have come into the situation of being tidally locked. So tidal locking means that you get one face of your planet facing towards the star at all times. In the same way that for the moon, we've got one face of the moon that faces us at all times, because the moon is tidally locked to the Earth. So I guess technically it means that the rotation period is the same as its orbital period. Now this happens with planets. I mean, Mercury is well on the way to being tidally locked itself, but it happens with exoplanets, especially if you've got planets close to a star and you've got kind of time. The only ingredients you need for tidal locking are gravity and time, and it will eventually happen. It will eventually happen to all the planets in our solar system if you wait long enough. But these planets, we do believe, should be all tidally locked to their host star. So that means that although you might be able to find some of them in the habitable zone, you kind of can extend your habitable zone out a little bit further than what you might normally. Because if you've got one sort of face of your exoplanet always facing the star, that face is going to get quite hot. If you've got the other face that's facing away from the host star all the time, then it's going to get quite cold. So it kind of makes sense that somewhere in the middle, you're going to have a nice temperature for liquid water to exist. It might not be particularly large areas of the exoplanet, but there's a good argument that you could say there's liquid water on most of these TRAPPIST planets. Which means that if you go study them, of course, and you've got 6 or 7 of them to play with, and if one of them doesn't turn out to be quite right, you've got a few more that you can carry on with. So this is probably going to be one of the very first systems that James Webb turns its gaze to once it's launched, because we are interested in that, then sort of picking apart what the atmospheres of these exoplanets might be. So to go planet hopping on TRAPPIST-1, you only need to travel sort of about 40 light years. We're coming to a sort of closer system now again. So coming back to our roughly 12 trillion pounds worth, although I guess your internal transfers between planets might be a little bit extra on top of that. It's not the record holder though, TRAPPIST. TRAPPIST has possibly 7 exoplanets. The record holder at the moment, just because I thought it would be interesting to show, is the Kepler-90 system. Kepler-90 has 8 planets, the same as our solar system. We haven't found any systems yet with 9, but I guess watch this space, and I think it might come eventually. Just a kind of a side note of what's quite cool about Kepler-90 is that Kepler-90I, the latest planet to be discovered in that system, wasn't actually discovered by a person. In fact, it was discovered by a computer. So it was a machine learning algorithm that actually found the final transit of Kepler-90I and spotted it in the system, which is also showing you just how much more advanced we are at finding exoplanets, that we can even ask our computers to do it now. The final exoplanet I wanted to sort of show you today is, again, one of these exoplanets that we didn't really ever expect to go out there and find. It's called PSO J318.5-22. Now you'll notice this breaks a little bit with the normal exoplanetary naming system, and it doesn't even have a small letter. And the reason for that is actually, when we normally name them, as we said, we have to start with the star name, then we just add some lowercase letters afterwards. With this exoplanet, it doesn't have a star, so we didn't even start with a star name. So this is a type of exoplanet we call a rogue planet, which means it's just free floating in the galaxy, and it's not associated with any stars whatsoever. Now, if you remember, I might have told you just earlier on in this talk, you said, well, hey, Emily, well, you told us that basically the way you detect exoplanet is looking for variations from the host star. If you haven't got a host star to look at the variations, how have we picked up this one? And the answer is actually, it's quite interesting. Normally when we look for, say, transits, we're looking at variations in the light from the host star. We can also look at things like variations in the Doppler shifts, or the gravitational forces between the host star and its exoplanet. And that's all dependent on the host star. In this case, what we're looking at is the gravitational influence of this exoplanet, but on stars that it's not even associated with. So just by using the way that light bends through the force of gravity, we can pick up these exoplanets, which are sort of floating through space all out there on their own. And these are, we think that there actually might be quite a few of these free-floating planets in our galaxy. We've discovered maybe 60 or so far. And it could be that there are many, many more, but they're just very, very difficult and very, very rare to actually pick up. Where they come from? Well, we believe that planets are formed around stars. So probably these are kind of orphaned planets, or they've been kicked out of their host star systems by some kind of violent event, something like that, and that's left them free floating through the galaxy. So these kind of stellar events aren't that uncommon. In fact, maybe lots of planetary systems end up kicking a few planets out, even in the process of formation. Even our own solar system, we imagine that there's at least a couple of planets that didn't make it into final orbits around the sun. So these things could be pretty common, which is quite exciting to think about. Now, this one's quite a big one. So if you want to sort of go to somewhere where you've got no star, therefore no light, therefore no day, then you might not really be able to land on the surface of this one. It's pretty huge. It's 6.5 times the mass of Jupiter, which is heading up into a category where you kind of become a little bit borderline as to whether you're a planet or a brown dwarf. And a brown dwarf's kind of a little bit like a star that never quite happened, a failed star, if you like. So it's kind of starting up to get to that borderline. So you might need to kind of have a nice spaceship, land on a beautiful ring and have a nice dance party there. Who knows? In any case, this is about 80 light years away, this particular rogue planet, so about 24 trillion pounds to get across to. To give you an idea of just how we find these things, there's two kind of ways, and this particular excerpt was found using both of these ways. The first way is we can look at the gravitational influence that it has, and this is how it was discovered. It's a process called microlensing. So what we do here is we look at the light of a star. It could be any sort of star that's just floating around their galaxy. And when there is a chance alignment of the planet passing in between us and that very, very distant star, then the gravity of the planet bends the light towards the planet Earth. So if we're observing the star over time, what we actually see is this very, very slight brightening of that star because of the way that some of the light that should have been shooting off sort of past the Earth in its path has actually been focused, if you like, towards us. So we see this little blip of the background star getting just a bit brighter. And from that, we can calculate the gravity, the position, the size of the free-floating planet. And then once this particular one was discovered, we went out there and went hunting for it, of course, to see if we could spot it. And this particular one we did. This is an image from the very, very far infrared. And I'm going to have to make a confession, I guess, at this point. This is the only actual picture of an exoplanet that I have in this entire talk. And it's perhaps not super amazing, I guess, not super inspiring, just a sort of a fuzzy red blob. And the only reason that we were able to spot this particular one is because it's so massive. It actually might have a little bit of leftover fusion when it was formed. It sort of got quite hot. Maybe it did a little bit of deuterium fusion, so not proper star fusion, but kind of just a little bit of warming from some off fusion processes, and therefore it's got a little kind of faint glow, sort of leftover from being this slightly warm from its formation. So that's how my only picture that I have to show you today of an exoplanet. And I promise you, I don't think there's anything actually that we've got so far that beats that in terms of photographing exoplanets. There's certainly nothing like all the ARCIS impressions that I've been able to show you. So let's take a little sort of a glance forward now. I showed you lots of Kepler exoplanets, and I've mentioned where we might be going next with with James Webb, the next sort of generation of hunters, and what TESS is actually doing. I'll give you a little bit of an overview now. So TESS was a follow-on mission from Kepler, so it's Transiting Exoplanet Survey Satellite. The main difference between TESS and Kepler is that TESS is actually looking at nearby stars, and it's actually scanning the entire night sky. So whilst Kepler was really quite focused on these quite faint stars, all in the sort of a bunched part of the constellation of Cygnus, TESS is a truly full sky survey. So it's doing both northern and southern celestial hemispheres. And it's looking at mostly bright stars instead of these faint ones. And the reason why we want to get onto the bright stars is because some of the Kepler star planets that we found were so exciting, but they're just so faint for us to do really good follow-up work with ground-based telescopes. And that includes the kind of spectroscopy that I'm interested in, doing really high resolution stuff. You can't do this stuff from space, so you're stuck on the ground, which means that your sort of limiting brightness is much, well, you need to work on bright stars really to do really good spectroscopy. So to do this, and to what we want to do with our spectroscopy is actually start to look at biosignatures, which means looking for chemical fingerprints in the atmospheres of exoplanets to see, can we, first of all, determine what the atmospheric composition is of some of these exoplanets. And we've started to do that reasonably successfully. For example, we've been able to spot water in the atmospheres of some of the TRAPPIST exoplanets. But the next step from there is to actually say, well, can we find a chemical signature that means that there must be life on this planet? Much like the discovery of phosphine on Venus recently, can we find a particular chemical element that means there must be life there? Now, it looks like the Venus thing is kind of fizzing out a little bit, unfortunately, but the race is on now to see if we can find some of these biosignatures. TESS is trying to find us some nice close exoplanets that we can really study well. And when it flies, the James Webb Space Telescope will be looking at, again, some of these discoveries from TESS and trying to pick out some of the most important chemicals that we can see and see if we can relate those to life. So that is really, I guess, where we're going. And it's a very exciting time, I think, because we really are just on this cusp of discovery. Biosignatures are happening, and well, the move towards finding biosignatures is very, very well developed now. The only problem, I guess, we're trying to overcome at this point is, well, first of all, we need to get James Webb up there. That seems to be quite a challenge. But the other thing is we've got to find something that's really unique. It's hard to find a chemical signature that seems to be only produced from life. And that's, I think, one of our next kind of astrobiological challenges, is to find something, probably not phosphine, but maybe something like that, that is really an indicator that is unique to having a life form on a planet. So I just wanted to leave you with a couple of exciting things to see where we're going with TESS and beyond. This was one of the first light images from TESS. So TESS flew in 2018. So it's just finished its first full mission cycle, spending 1 year in the northern celestial hemisphere, 1 year in the southern, just back on the southern again now. And this is one of its very first images, which just made us all, as both variable star astronomers and exoplanet astronomers, really excited. This was just one camera, so TESS has 4 cameras. This is just an image from part of one camera, and there's more than 10,000 unique stars in this image that we can track, monitor for variability, monitor for transits. And it's just such a beautiful thing. I just love just looking at these kinds of images coming from TESS. Very, very exciting. And TESS is successful. TESS has found something like 82 exoplanets to date, and it's finding, as it seems to be the theme with exoplanetary science, new and weird exoplanets just along the way as well. These are 3 of the first exoplanets that TESS discovered, yet all of them are a bit weird in their own way. So the first one, LHS 3844b, this seems to be a rocky planet that's missing an atmosphere. We don't know why it's missing its atmosphere. That's a bit of a puzzle. Pi Mensae C was a planet that we didn't think should exist because it's got other exoplanets in kind of very, very close big orbits, which means it should be gravitationally unstable and it should have been kicked out of its system, but it's there. And HD 21749b is a sort of a Neptune-like exoplanet, but it's actually a bit too warm. So it's kind of encroaching into the inner part of its solar system, and it's kind of slushing up. So instead of being an ice giant, it's kind of a warm, slushy giant, which is a bit of a mystery. So there's loads more in exoplanetary science, and it just seems like every discovery seems to ask more questions than it answers. And that's, I think, the hallmark of a very, very exciting new developing research field. So that's where I'm going to end the formal part of my talk today. Just a couple of sort of, I guess, advertisements, if you like. As Alan mentioned, I'm the director of the Astro Campus at the University of York. We are a teaching and outreach observatory, and we love to do link-ups, whether that's with other local astronomical groups or other community groups. If you want to get in touch with us and hopefully post-COVID come and visit us, then please do check out all our details on the internet there. All the exoplanetary travel posters that I have shown in this talk come from the exoplanets research through NASA. So they've got amazing resources. Do have a look. You can get absorbed for hours and playing with some of the exciting tools there. And finally, if you're not sick of my voice already and you want to see more of my own personal outreach work, then I have a podcast which is called Syzygy. And so you can have a look on syzygy.fm. We just recorded an episode last week, which was all about planets and quasars, which are sort of some new discoveries. And we're about to record next week a tribute to the Arecibo Space Telescope, if you want to hear more about that. Otherwise, thank you very much. And I'm very, very happy to answer a few of your questions.
Thanks very much indeed, Emily. That's really good. I know that there's a couple of questions that have already sort of come through on the sort of the chat system. What we'll actually do is, if I can get a question in first, and then what we'll do is Andy, that if you can look at the screen and then read out the sort of the questions. If you want to utilise the chat facility, then you can do so, and then Andy will read your question, and then Emily will no doubt be able to answer it for us. But, so thanks so much indeed, Emily. Can I ask a quick question just with regard to Ariel? I know that some amateur astronomers are involved with projects to checks of transit curves on that. Is that anything that you're involved with as well?
Sort of peripherally. So I have some project students that I work with at York who are doing follow-up work on transits from ground-based facilities. I think it's pretty astounding. I mean, we've got access to a remote telescope that's only it's a 6-inch remote telescope, and we're still able to pick up some of these transits, which I think is just extraordinary and a testament to how much kind of low-cost and amateur equipment has developed, I think, even over the last 5 years or so, to be able to do these precision observations, which I think we would have all said would be unheard of sort of maybe a couple of decades ago. So yeah, there are lots of projects to get involved with. I'm not involved with any particular individual one, but if you want to try catching exoplanets and you've got a small telescope, I don't see any reason to, there's nothing prohibiting people trying. There's great resources out there that can tell you what's in your night sky, what transits you can pick up. And I think I even spotted on the BAA website a tutorial about transit photometry. So I think you've got some nice resources there too.
Thank you for that. Andy, can I hand it over to you to read out some of the questions?
Yes, sure. And thank you, Emily, for a fascinating talk. So to people who are attending on Zoom, you can ask questions using the Q&A button at the bottom of your screen. And if you are on watching on YouTube, then I'll keep out an eye for any comments which come in from there. The first question we have is from Diane, and it's regarding Kepler-16b. Do you have any thoughts as to how its atmosphere is being affected by two types of solar radiation?
Oh, that's a really good question. So 16b it's reasonably close to both stars. So most of the time, if you imagine kind of the energy that's coming from the stars would just be summative, right? So you get energy onto the atmosphere, which comes from star A, and energy which comes from star B. But because you would get, I think these two stars will eclipse in this particular system. So that means sometimes star B will hide behind star A. So you'd get quite a significant drop. So you might get these kind of odd, kind of really cold periods because you've lost some of the energy from one of the stars. Now, in terms of how the atmosphere then gets affected, that would change things like how the winds in the atmosphere get driven, because winds are all based on temperature changes. So if you quickly drop your temperature, you actually would generate enormous winds through the atmosphere. So I actually think probably it would make the exoplanet a nastier place than it would have been otherwise. But these are just sort of my first speculative thoughts. I haven't seen any sort of detailed research on it, but yeah, it's quite an interesting system.
Thank you. Next, we have a question from Adam Fairhead. The free-floating planet you showed has a density of 3 times Jupiter. That sounds dense for either a Jupiter-like planet or even a brown dwarf.
That's a good question. So I didn't put any uncertainties on my figures, which was maybe very naughty of me as a teacher who gets all my students to do uncertainties all the time. I'd imagine, I can't remember them off the top of my head, but I imagine the uncertainties are probably moderate on these kind of exoplanets. The masses you can determine reasonably well using microlensing, but the radii of these exoplanets are quite hard. So first of all, I think there's a bit of wiggle there. But I think it's just all down to compositions as well. I mean, our Saturn and Jupiter are mostly primordial elements. So we're looking at hydrogen, helium as their primary elements, whereas if you just happen to form a slightly bigger core from your accretion disk, then I can see how the densities would, I don't think they would necessarily scale up as you push the planet size up higher.
And Diane says thank you, and also a very interesting talk. We have a question from Stephen Brown. Have any exoplanet moons been discovered?
Oh, another very good question. Actually, sort of yes and no is the answer, which I guess is not very satisfactory. We did find a system a couple of years ago. I don't remember what it's called, but it was a system where you had a planet which was about the size of Uranus orbiting around a planet which was about the size of Jupiter. And so I was sort of speculative at the time. I thought, well, is this actually a moon, an exomoon, or is it a kind of binary planet system, two big planets like that together? Now, at the time, they called it a moon, and it was the first exomoon discovered. Unfortunately, I think it was only about earlier this year, they sort of hashed through the data, and it's now thought that actually there are 2 separate planets and they're not orbiting each other. So we're back to having no current exomoons, but there's no reason why they shouldn't exist. They're just really hard to find.
And then we have a question from Janice McLean. Thank you for a great talk, really interesting. Do you think that the discovery and growing knowledge around rogue planets will have an impact on our current theories on the development of solar systems? I guess it is likely we had a few migrate from our own system.
Absolutely, yeah. I mean, understanding even just the evolution of our own solar system is really hard because we've only got obviously the current day system to look at, and then other exo systems which are being formed, and you kind of try and rewind, I guess, what we see now to what we think might have happened in very early times. It's also very chaotic, so very small changes in solar systems can have big effects. But from different models that I've seen of our earlier solar system, many of them do include other planets which simply aren't there anymore. This is one of the explanations, for example, why Mars is actually probably a bit smaller than it should be, and why the asteroid belt maybe still exists, because there was some disruption gravitationally between Jupiter and some other inner planets, including Mars, which may have prevented the formation of kind of a proper sized Mars. But yeah, I think learning more about these these rogue planets will help us trying to pin down statistically, at least, how often planets do get ejected from their host systems.
And next, we have a question from John Murrell. As TESS only observes the same field for around a month, does this bias the results to planets in short orbits?
Absolutely, yes. In terms of initial discoveries, so when you only stop and stare for about a month, you probably, well, even if you get one transit, of course you can't determine the orbital period. So what we have is kind of a few systems out there to kind of nail down some of the TESS discoveries. The first one is what we call TOIS, which are TESS objects of interest. So if there is an exoplanetary transit detected from TESS, that can go out to the community, and there's lots of follow-up projects, survey projects around the world that can follow these targets and see if we get second transits to find out how short the periods are. Also, TESS has just now flipped back again to the Southern Hemisphere, so we're getting another round. So that means we'll have sort of 2 months of data. And I get another kind of interesting point with TESS is that in each hemisphere, it also has what we call continuous viewing zones, which means it actually does get 12 months of data of these areas of sky. And those continuous viewing zones overlap with what will be the continuous viewing zones of the James Webb Space Telescope. So it's all kind of designed to hook into each other. So when James Webb flies, hopefully we'll know of quite a few planets in those zones that might have these longer orbits.
Thank you. And we have a question on YouTube from Richard Miles. Any thoughts on whether rogue planets can make up a fraction of the so-called dark matter in the universe?
Yeah, that's also a really good question. So we did consider dark matter and sort of just planets in general as being, rogue planets and planets in general as being a potential dark matter source. And this was something that was particularly explored, I guess, in the 1990s, particularly under sort of programs that were looking for MACHOs, massive compact halo objects, so just bits of mass in the galaxy. Now, it turns out if you do the sums on even kind of the most ambitious estimates of how many of these rogue planets there are in the galaxy, and even how many planets you might have in the galaxy altogether, it doesn't come, unfortunately, anywhere near the kind of mass that you need for dark matter. So and in terms of sort of percentages, I believe it's kind of less than a fraction of a percent of what we need for dark matter. So unfortunately, they got ruled out.
And Steve Brown says, thanks, very interesting. And then final question from Michael Omar. Do you also apply statistical assessments on whether life may be detectable on an exoplanet, irrespective of any biosignature being detected? In your opinion, what are the odds of finding life?
Oh, there's an interesting way of doing this. There's a very sort of back of the envelope way that's been done to look at what the probability is of finding life in our galaxy. And you might have heard of something called the Drake equation, which is a little bit, I guess, taken tongue-in-cheek in these days, but it was an equation set up by Frank Drake just to try and put a statistical value on what is the likelihood of finding a life. And in his case, with the Drake equation's case, it's about communicable life. But what we really, even if you pair it back to kind of, could you find sort of pre-cellular life or things like that, then the arguments you can make astronomically are quite well known. So in the last sort of 30 or 40 years, we've been able to nail down the astronomical sort of side of the statistics, meaning we have a pretty good understanding of how many stars there are in our galaxy, how many stars which would be suitable for planets to be habitable. Then we've with Kepler and so on, we've been able to nail down how many planets are in our galaxy, and now even how many planets are likely to be found in these Goldilocks zones or habitable zones around their host stars. So I would say the astronomers have done quite well, actually, in determining all these things. The problem is the biology is actually, we don't have any statistics from the biological side. We have ideas about how life sort of sprang and evolved on the surface of our planet. But even if we have a fairly good understanding of that, it's a sample of one, which is not great. So actually coming to a conclusion about whether life would arrive, even if you've got a nice habitable planet, that question is so open, you could kind of pick any number between probability of 0 and 1, and who knows whether you're right or not. So yeah, I think I go against the grain of a lot of astronomers in my own opinion, and that's, I actually don't think don't think it's going to be easy to find life. I don't think it's maybe as abundant as we once thought. When we found out that there were hundreds of billions of planets in our galaxy, I think people got really excited and said, well, that's hundreds of billions of opportunities for life. I think that's true, but from conversations I've had with biologists, to me, it seems so unlikely that life arises, that kind of set of conditions sets up so that you get the arrival of life, that I'm sort of wondering, actually, even with those large number of planets, it might not be that likely that life appears, but that's really my own opinion.
Thank you. And actually, we'll sneak in one final question from Andrew Grant, as it's the last one there, which is, are planets that are not orbiting around a star actually planets, considering that orbit around a star is one of the criteria for being a planet?
Oh, yeah, very good again. Okay, so I'm going to maybe shock everybody and say we actually don't have a formal definition of an exoplanet. The only thing we really have a formal definition for is what a planet is in our solar system, and that was famously determined by the IAU, and that's what Pluto got the boot. So we have criteria for being a planet in our solar system. There is no official criteria for being an exoplanet, because I think partially, as soon as you start to draw up a list, you immediately find examples which counter that list, which you sort of feel should be exoplanets, like rogue planets, for example. So although I've seen some drafts from the IAU about what they might like to try and define an exoplanet as, nothing's gone through. So we end up in this kind of position where if it looks like an exoplanet and behaves a little bit like an exoplanet, you feel like you should call it an exoplanet, then it's probably just an exoplanet then.
And many thanks again for your fascinating talk on this rapidly growing field.
Thank you.
And
thank you all for the excellent questions.
Yes, great. And I'll pass on to Philip if he's able to.
Hello.
Come on now. Great, thank you, Philip.
That was a wonderful talk, Emily.
Very festive, Philip.
Thank you. Well, happy Christmas, everyone. So I am here to give you, over the next 25 minutes or so, an overview of what is in the sky at the moment and what we have to look forward to in the coming weeks. So this is the traditional BAA meeting Sky Notes. So you should now be able to see my presentation. Can you confirm, Andy?
Yes, that's all there. Thank you.
Excellent. So it's a great pleasure to be doing this, particularly coming after Emily, who supervised my Master of Physics project at York, and she was a fantastic supervisor. So it's a pleasure to be sharing the bill with her. Last time I think she saw me give a presentation, it was one that was marked, so I'm hoping she's not marking me now, but I will find out, I suppose. So I'm going to begin with this beautiful picture of the Pleiades M45 in Taurus open cluster, which was taken by one of our most prolific imagers, I think, Mary McIntyre. And she's done a lovely job of capturing both the star cluster and the reflection nebula, which may or may not be associated with the cluster. There's been a lot of debate about this in recent years. And she's captured it in conjunction with a holly leaf as well. So if we continue, apologies, my malfunction there. Okay. Continuing from the moment this talk finishes, which should be around 4 if all goes well, looking southwest, we've got Jupiter and Saturn forming a lovely pair quite low above the southwestern horizon. And this is an image again by Mary McIntyre, taken on the 22nd of November, showing the International Space Station passing the 2 planets. And this is what we should be able to see in about half an hour. So wherever you are in the UK, if you are in the UK, you should be able to see the ISS going overhead, reaching its peak altitude at around about 4:31, with depending a bit on where you are. If you're in the south of the UK, it will be just about at the zenith. Where I am, it's more like 50 degrees, and it'll be progressively lower the further. I should add the time in Yorkshire. But it's making a succession of evening passes at the moment, so do not miss the International Space Station. And now the traditional thing with SkyNotes is to begin with our sun, and it is a recent SkyNotes tradition to begin with a picture of a completely blank disk. Of course, it's been extremely quiet this year after reaching minimum. And the first straggling signs of the new solar cycle 25, just started to begin in recent months, but things really took off in November. Firstly, with active region 2781, which is a lovely picture of it by Brian Halls in early November, and then the real excitement began with AR 2786, which is the large spot. You can see my cursor there. This was it just coming over the limb on November the 23rd. AR 2785 had appeared the previous day. And it's still on the disk. It's just going over the western limb now, but it's still visible. And it really is a monster. You can see in this lovely image by Philippe Tossi, you can see the Earth given for comparison of scale, and it is yes, it's still visible. And at the moment, we have a new sunspot group, AR 2790, which has been putting out some flares in recent days. So by the 29th of November, we actually had 6 active regions, sunspot groups, in the southern hemisphere of the sun, which is quite amazing. And the scale of this one was quite remarkable for this early in the cycle. It actually became an F-type group, which is because it spanned more than 15 degrees of longitude, which is the largest type of sunspot group you can hope to see. And here are the 2 active regions, again caught by Michael Stefanou, who observes from Athens. Pete Lawrence in Leicester also got this spectacular picture on the 26th, showing a sun that's actually doing some stuff. And meanwhile, the Solar Dynamics Observatory, using its atmospheric imaging assembly, caught this footage. This was on the 23rd, so you can see the 2 active regions coming around the corner there, the limb, I should say. And you can see that we've got an ejection here. This is in ultraviolet. This is a combined image of 7 channels of ultraviolet wave bands. And where you've got flaring of this kind, you can expect to see some sudden ionospheric disturbances. So if you do not happen to have the Solar Dynamics Observatory at your disposal, you can observe at very low frequency, do some radio observations, and there's more information about how to get involved with this from the BAA radio section page. This is provided to me by the director of that section, John Cook, and you can see the solar flares are categorized between A, B, C, M, and X, where A is the smallest type. Astronomers do not really understand the alphabet, as has been shown by both this and the spectral stellar classification system, of course, which begins OBA. But at least this one does start ABC, so some credit is deserved there. So you can see the sunspot number is this solid line, and the flares detected roughly follow that. So in recent months, that's been extremely quiet, but things have started picking up in October. And where you have a more busy sun, you might expect to have some aurora. But aurora has actually been quite quiet since the last meeting. This is a nice image by Denis Paczynski at Tarbetness in Scotland, and taken on November the 21st. But things have generally been quiet, and normally you'd expect noctilucent cloud activity, which is also monitored by the aurora and noctilucent cloud section of the BAA, to be picking up in the southern hemisphere at this point. And this is a lovely image from the AIMS satellite showing ice in the mesosphere, which should show the extent of noctilucent clouds forming in that region of the atmosphere around the southern pole at this time of year. However, this picture is not from this year. This is from last year. This is this year. And you can see the profile of Antarctica there. And there are no noctilucent clouds at all over Antarctica currently. And this is coinciding with extremely cold temperatures in the upper atmosphere above the continent, and also the hole in the ozone layer being at a record-breaking extent. This has come out in the last couple of days. So something strange is happening over Antarctica. And I cannot mention Antarctica this week without trumpeting again that our visual observations coordinator of the comet section, Jonathan Shanklin, has just this week had a glacier named after him. This is in recognition of his work with the British Antarctic Survey, and in particular for co-discovering the hole in the ozone layer. So congratulations go once again to Jonathan. If you're wanting to observe the sun and you're in southern Chile or southern Argentina on December the 14th, then you'll be disappointed because the moon will be in the way. This is a total solar eclipse happening at around about 4 o'clock UK time, universal time. And this is an image not of this eclipse, of course, because unfortunately Nick James has not solved the problem of time travel, but one he took again from South America last summer. So few people are expected to observe this because of the travel restrictions around COVID-19. But it can be observed on NASA television, of course. For meteor showers, we've got 2 lovely showers coming up, the Geminids and the Quadrantids. But the focus is on the Geminids, firstly because they are the first, and also because they are especially favorable this year. So this is a nice picture by Richard Fleet of the Geminids emanating from the radiant, which is in Gemini. You can see it just to the north of Castor there. So they'll be active from between December the 6th and the 17th, and they will be peaking on the night of December the 13th at around about 8 p.m. I mean, you can expect to see, well, the zenithal hourly rate, so the hourly rate that you'd have if the radiant was at the zenith directly ahead above, would be around between 100 and 120. Unfortunately, this is of course never quite the case, but observed rates are still between 70 and 80 per hour. And though it's a really lovely shower, partly because you've got lovely slow meteors. They only enter the atmosphere at about 35 kilometers per second, which might seem fairly fast. But if you compare that to the Perseids, which arrive at more like 60 kilometers per second, you really get to enjoy the Geminid meteors that bit longer. You've got a chance to, a Perseid you can see it out of the corner of your eye, and a Geminid you can actually turn and take a proper look at. So it is a lovely shower, and we're very lucky, as you can see from when that solar eclipse was happening. The moon is new on December the 14th, so it's perfect timing, no interfering moon. And more widely, if we're looking over timescales of years, we're still at a favourable time for observing the Geminids, because they have only been known for the last 200 years or so. We're moving through a meteoroid stream, and we're at about the densest part now. So in the coming decades, activity might begin to tail off as we leave that. The meteoroid stream is not the result of a comet, as you'd expect from most meteors, but in fact this object, which is 3200 Phaethon, and it is a near-Earth asteroid, which comes within has a period of about 1.4 years, and it comes to within only 0.14 astronomical units of the Sun. And it was only realized in recent years that this appears to be the source of the Geminids. This is an illustration by Paul Doherty, an artist's impression of what it might look like when it's near the Sun. This was actually then observed more recently by the SOHO spacecraft, and in 2009. And this is a more recent observation from Hubble in 2013, and you can see that it does indeed sport a tail when it's at its closest point to the Sun. So there's some form of disintegration mechanism happening there, but it's rocky, not icy, which explains the slowness of the meteors, perhaps, the rocky nature that you see. later we've got the quadrantids on January the 3rd and 4th, but unfortunately at that point they're both, the best time to observe them will be at about antisocial hour early in the morning, and at that point, sadly, there will be a waning gibbous moon, which will be somewhat in the way. But before then, we have a very exciting astronomical event, which is the end of the world. The world will end on December the 21st, it seems, or at least that is the case according to this report, which appeared in the Express, which is not necessarily the greatest source of astronomical information. This refers to what is a very special event, the Great Conjunction, as it's being called, between Jupiter and Saturn, who have been approaching each other over the past year. But on December the 21st, they will only be 6 arc minutes apart. So that's only 1/5 of the distance, the diameter of the full moon. And the top image here gives you a telescopic field of view for that day on December the 21st at about 5 p.m. And low in the southwest, you'll be able to see the 2 planets in the same field of view, and you can see their assortments of moons there too. But it'll be, if you miss it on December the 21st, because let's face it, it'll probably be cloudy, it'll be observable a few days either side, where they will be similarly very close. And it's a really exciting opportunity to see the mechanics of the solar system at work, especially as close conjunctions between Saturn and Jupiter only happen every 20 years. Last one was in 2000, the next in 2040, and a really close conjunction of this kind has not happened since 1623, when Jupiter also occulted Uranus, but unfortunately Uranus wasn't discovered for another 150 years, so I doubt that was seen. If it is completely cloudy, then go to the University of Exeter's website, the Great Conjunction website, which there's an address there, and they've got lots of great videos about the conjunction and some outreach material, including for kids, and there'll also be live streaming of the conjunction. Moving to the moon, I love, again, talking about the mechanics of the solar system. I love this collection of sketches by Mary McIntyre. These are pastel drawings taken over the last couple of years, showing slightly different librations, so the orientation of the moon is slightly different between them, but it's a lovely illustration of the lunar phase cycle. And it reminded me of an image or succession of images taken by Emma Alexander in Manchester earlier this year. It's a similar idea, but of course in May we had that spectacular run of clear weather in the UK, and it's actually very rare to see a clear run of 7 consecutive images of the moon, which is quite hard to get in this country. David Artistey recently took in November this lovely image of Mare Orientali, which is a 900-kilometer diameter basin, just visible at certain times, again depending on the libration or orientation that we see. And he's captured Montes Rook and Montes Cordillera, which are these huge concentric rings of mountains around Mare Orientali, around the basin, formed by shock waves when it's impacted. We can see the phases of the moon here. This is taken from the BAA journal, which I edit. And throughout the Christmas period, the moon will again be well placed in the evening sky. It's nice to be observed at a nice social hour as it waxes. And Bill Leatherbarrow of the lunar section is calling for more observations of at a low angle of illumination to capture subtle volcanic features like domes and wrinkle ridges, which has formed a really exciting area of research for the lunar section in recent years. And this brings me neatly to Chang'e 5, the spectacular Chinese mission to collect a sample from the moon, which arrived on Tuesday and has lifted off on Thursday. I think we're so used to more distant missions, it's amazing how quickly a mission to the moon all happens, and then it will be returning to Mongolia in the coming weeks. It's worth mentioning that tomorrow, Hayabusa 2, the Japanese mission, will be returning with a sample, if all goes well, from an asteroid. So we've got 2 samples from celestial bodies incoming over the coming days. Chang'e 5 landed at Mons Rumke, which is a huge volcanic complex, well shown in this image by Bill Leatherbauer, which is really easy to observe in a small telescope. Nick James, amazingly, managed to capture Chang'e 5 on its way to the moon. This is it 350,000 kilometers away, and he did well to capture that. It was then about magnitude 8, so surprisingly bright, actually. And then, just to outdo himself, he then also captured Surveyor 2. This is the Centaur upper stage of the rocket that launched Surveyor 2 in 1966, another mission to the moon, which unfortunately failed. But here the upper stage has returned to our skies in recent months, at first mistaken for an asteroid. Moving to the planets, Mercury and Venus have been morning objects. They're now very tiny, as both are nearing superior conjunctions. Mercury will do so on the 20th before becoming an evening object in January, but it has a very tiny disk showing a small phase. This was taken in November by Peter Tickner. And again, Venus is showing a gibbous phase, but after being a spectacular object earlier in the year, it is now, although brilliant at magnitude -4, a difficult telescopic object. Lots have been happening on Mars recently. This is another image from David Ardity showing Syrtis Major, that triangular feature in the middle. Spectacular drawings from Paul Abel too. And this is a lovely collection of images from Mark Phillips in Edinburgh, showing the apparition this year. You can see the South Polar Cap, which is at the top, of course. These are all oriented as if in a telescopic field of view, with north at the bottom. We like our orientations like we like our alphabets, all nicely mixed up. And the excitement in recent weeks has been a dust storm. It started on November the 11th in the Mali-Erythraeum region. This is now subsiding, but again, this is well shown in these images from David Basie on 22nd of November. And this is a spectacular image from Damien Peach, which he's actually managed to capture Gale crater. This is using a 1-meter telescope in Chile remotely, and he's captured Gale crater just here, where Curiosity, the rover, is, and it's only 150 kilometers across. So it's an astonishing image for an amateur to take, which he took with Enrico Ensman. And don't forget the Mars Mapper tool on the BAA website to help you see what you can observe on Mars. But Mars is now shrinking, although well placed. It's still it's at about 15 arcseconds now, getting smaller. Much has been happening on Jupiter this year, but it too, as we've seen, is very low in the evening. It's only about 12 degrees altitude. But the Juno spacecraft recently did its 30th perigeo sweep past the polar regions of Jupiter, and captured, even in quite quiet areas of Jupiter, picked up a lot of detail. Saturn, pictured here, this is the image from Trevor Barry in infrared, is similarly affected by very poor seeing. And Uranus remains an evening object, and some detail can be made out. This in November the 27th from Manus Cadasis does show some brightening of the northern hemisphere. Comets are rather thin on the ground, but we have C2020 F3 Erasmus. In this image from Peter Carson, Erasmus is currently around magnitude 6.4, but it's and it's in Libra, which is just about visible as a morning object, but it's at a low declination at -20. Meanwhile, Comet 29 Schwarzmann-Bachmann continues to surprise with its regular outbursts and semi-regular super outbursts. There's a huge one on November the 19th. This is the latest information from the Comet section, where Richard Miles is running a project to observe it. So if you want to observe 29P, then get involved with that on the Comet section website. And the one on the outburst on the 19th is the best outburst ever observed of the comet. And you can see that it's expanding coma taken as a second smaller outburst on the 23rd in these comparison images by Nick James. On December the 8th, 29P will actually occult a 14th magnitude star. So this will give us hopefully even more information about its nucleus. We know it's a huge nucleus by cometary standards. It's about 64 kilometers across. But being able to profile it in this way by getting a light curve from occulting this star might be extremely helpful, and this is perhaps the first time that this has been done, and it will be visible in Scotland if it is clear, of course. So again, look on the BAA website for instructions on how to observe that. Very excitingly, we have a nova in the sky, an 8th magnitude nova. This is V1112 Persei, which appeared on November the 25th. It was discovered by Seiji Yuda in Hokkaido in Japan. That's nearly 11th magnitude, and it's since rapidly brightened, and it was confirmed by Jeremy Shears and Gary Poyner in minutes of its discovery being announced. So if we zoom in, we can see in this lovely image from David Swan what you might be able to see through a telescope or even binoculars. It's a lovely, easy to observe nova. And this is a picture that I took yesterday. No, it's not. This is an artist's impression by NASA, showing the mechanism for a classical nova of this kind, where a material accreting onto a white dwarf suddenly triggers runaway nuclear fusion, and you get this huge explosion, an expanding envelope. And that expanding envelope, emitting as it does so, can be observed as a spectrum, which we'll see in one moment. So this is the light curve. You can see there's one observation there from the All Sky survey for tracking supernova, which was detected before it was officially discovered. So it's since been added to the light curve. And you can see it's currently plateaued, so at around about 8th magnitude. So do go out and take a look. David Boyd got this lovely spectrum using a LISA spectrograph, which Emily will be very familiar with, as we have one at the Astro Campus at York. And he's got the hydrogen Balmer lines, hydrogen alpha, beta, gamma, delta, and epsilon. And he's also got helium lines. But the thing I find really exciting here is that he's got P Cygni type line profiles. So this is due to absorption. If you look closely at those emission lines, you can see dips to the blue side of them, and that's due to blue shifted material racing towards us and absorbing light at those wavelengths as it does so. So you can actually really get an idea of the dynamics of what we're seeing. Alpha Orionis Betelgeuse, of course, as it's better known, continues to be to spring surprises, perhaps, or does it? This star, of course, faded in winter, and it is now winter of last year. It's now roughly plateaued, as you can see from this light curve. The gap there is when it was lost to the sun, but it seems to be behaving itself, keeping fairly steady. It's a really easy to find variable star, of course, which makes it all the more exciting, seeing the constellation of Orion becoming unfamiliar. So and in the latest journal, we have a paper from Mark Kidger about Betelgeuse, in which we can see it, in which he predicts a fade in April of next year. Briefly, there's also a dwarf nova type variable star, which the variable star section is monitoring. This is IX Draconis. So do take a look at that, and again, more information on the variable star section website and in their circulars. It's being monitored by TESS, which Emily mentioned, but it is out of TESS's fields of view for the next couple of months. Amateurs are being called in to observe both its normal outbursts, which happen every 3 to 5 days, and also longer super outbursts every 60 days or so. And Chi Cygni is another variable star that is well placed, even though we think of Cygnus normally as a summer constellation. It is still available to observe, so do take a look at that. Not just stars changing, we actually have a disappearing nebula recently. Gilbert-Abington's nebula vanished. This is associated with the star PV Cephei, which I'll just indicate with my cursor there. And Nick James has shown its variable nature there. I'm just going to wrap up with exoplanets, and I apologize, I've gone a little bit over time. So it's again returning to the topic that Emily was talking about, and amateurs can indeed observe exoplanets, even with small telescopes. So as was mentioned in the question and answer session there, it is the exoplanet division of the asteroid and remote planet section, which is the exoplanet division is led by Roger Dimmock. is working with these two missions, Ariel and Plato, both yet to launch. In the case of Ariel, what is needed is transit observations to confirm transit times, to ensure that the craft is pointing in the right place at the right time. And Plato will require transit observations to confirm discoveries. So do look at the Exoplanet Division website for more information on this. And here are some exoplanets which you can observe in transit, or indirectly observe, in the first 6 months of next year. And all of this is available in the BAA handbook, that actually predictions for exoplanets, which is hugely exciting. Sorry, I appear to be going backwards. Let's go the right way forwards. And there's lots more information on the Exoplanet Division website. And do look at their newsletter, Infinite Worlds, which is if you haven't signed up for that, then do, because it's quite exciting. And lastly, I cannot help but plug the BAA journal, which will be available as a PDF download later today. And the December edition has a Christmas quiz, and we're lucky to have the First Light Optics have donated some wonderful prizes, as well as we've got the Stargazers Almanac as a third prize. So do, even if you can't answer all the questions, do submit what you can, and who knows, you might win when the competition closes in January. So I shall finish. I apologise, 5 minutes late, by wishing you all a very happy New Year and a Merry Christmas, and most importantly, lots of clear, dark skies in the year ahead.
Thank you, Philip, for an excellent Sky Notes. I'd also say a big thank you to Philip for all the work he does on the journal as our journal editor. I know how much effort goes into that, and every couple of months. We do have one question, but I'm not sure how easy it will be for Philip to organise this, which is Stephen Brown asking if you can arrange for the sky to be clear around the peak of the Geminids this year.
Yes, that is no problem. Yes, I will. I will do a dance, a clear dance to hopefully bring that about. So the best time to observe that will be just after, when in fact the Geminids tend to peak in terms of the brightest meteors. They tend to be after the forecast peak. So later on that night of the 13th will be, and into the early morning might be a great time to observe them. So I'll do my dance then.
And he's also very pleased with the Mars mapper we have available.
Yes, that's brilliant, isn't it? Really useful. I was using that just a couple of days ago.
And I'd like to let everyone know that in just under 2 weeks' time, on Wednesday, the 16th of December at 7 p.m, we have our next webinar, which is How to Image the Sun in 3 Wavelengths by Sherry Lynn Carl. And let's all hope by this time next year, we'll be able to meet in person for the Christmas lecture once again, and hopefully sooner than then as well. And so I'd just like to take the opportunity once again to thank Philip Jennings for his talk on Sky Notes, and also to Dr. Emily Brunsden for her talk on the exoplanets, which was fascinating. Thank you all, and I hope to see everyone soon.
Merry Christmas.